So then, so one of those becomes psi 1, psi 2, sigma plus 1, 2. And of course, the other one is psi 1, psi 2, sigma minus 1, 2. And as it turns out, we can categorize these. We can group these together. And I'm going to group them together as following. I'm going to group these three together. And we'll keep them as a triplet. And I'm going to group this one together. And I'm going to call it a singlet. Okay? And so why did we group them together in this way? Well, once again, Pauli tells us that if we switch the labels of the electrons, if we switch their positions, the wave function has to change sign. Okay? Well, when we look at this sigma minus 2, 1 state, right? So we know it was written as sigma minus 1, 2. So what happens when we switch those positions? Okay? Well, when we switch those positions, I get the following: 1 over root 2 of, and so now follow me here, right? So this is going to become now alpha 2, beta 1, and this one's going to become minus beta 2, alpha 1. So let's put all that together. So that's going to be alpha 2, beta 1, and then minus beta 2, alpha 1. Okay? And if I do a little bit of algebra on this thing, I'm going to factor out the negative sign, factor out the negative 1 over root 2. And then when I do that, I get that this term will become positive and this term will become negative. So this is my positive term. And now I'm going to write that as alpha 1 beta 2. So it was written as beta 2 alpha 1, but because this operation is just multiplication, I can write it in the other order. And now this term, because I factor out the negative, is going to be negative. So that's going to be written as, let's see, I'll write that as negative beta 1 alpha 2. And now let's compare this really quick. Okay, alpha 1 beta 2 minus beta 1 alpha 2. Alpha 1 beta 2 minus beta 1 alpha 2. Okay, so let's see. What happened here? Did I make a mistake in my math? Oh, no, I did not make a mistake in my math because I have a negative sign right here. And so as it turns out, all of this will just equal negative sigma plus 1, 2. So that means, let me rewrite that up here, sigma minus 2, 1 equals negative sigma plus 1, 2. And because that switches signs, that one is the only acceptable wave function to describe my paired up spin state. So what does all of that mean? Well, what that means is when we have two electrons, okay, two electron system, we get two, count them, two possibilities for spin states. Those possibilities are a singlet, which I've highlighted in blue, and that singlet, the sigma 1, sigma 2, sigma minus 1, 2, that's the only acceptable wave function to describe the spin pair, okay? But what does that triplet correspond to? Well, that triplet could be both spin up or both spin down or some superposition, which I'll go ... I'm going to put like, well, I can't really draw this very well. Or I'll just write this as the following. So we know that that's not acceptable. So really what it means is we've just switched the labels. Okay? So like if I put 1, 2, 1, 2, or what we have is 2, 1, or 2, 1. Okay? So, 2-electron system. 2 possibilities. A singlet state, which is a pair, or a triplet state, which is not paired. So that's the biggest conceptual detail I want you to take home from this, is recognize that a triplet state, even though it seems kind of confusing calling it a triplet state, it's triplet because it has to do with superpositions and uncertainty. Or the singlet state, which describes an electron pair. Okay, so moving on. So we recognize that what this means now, of course, for helium, there's only going to be one acceptable wave function in this fashion, because we remember that helium is 1s2. And because Pauli tells us no more than 2 electrons may occupy the same orbital, and if they do, their spins must be paired. So helium is a closed shell atom that must be described by a singlet spin state, which means its wave function has to be sigma 1, sigma 2, sigma minus 1, 2. And where does all of that come from? Well, it comes from what we call here this determinant, this matrix, okay? This matrix of possibilities where we have psi 1 alpha 1, psi 2 alpha 2, psi 1 beta 1, or psi 2 beta 2. And so if you recall in solving this thing, and the 1 over root 2 is our normalization constant, right, we do the diagonal, okay? So that's going to go as psi 1 alpha 1, right, times psi 2 beta 2, and then minus the other diagonal, which is going to be psi 2 alpha 2 times psi 1 beta 1. And if we were to do algebra on this thing and factor it out, right? Let's do that. We can factor out the 1 over root 2. We can factor out the psi 1, psi 2. And what we'll be left with is alpha 1 beta 2 minus alpha 2 times beta 1. And this is equal to our sigma minus 1, 2 wave function, okay? So for helium, only one acceptable total wave function because of the spin states, all right? If we were to do this for a helium excited state, which I'm going to show you next, so perhaps, right, 1s1, 2s1, and we were to go and do this matrix of possibilities, we would get 3 possibilities to describe this. And I'm not going to go through all of that.